Okay. So the next speaker is Egor Shelukhin from Montreal, and he will talk about a symplectic Hilbert-Smith conjecture.
Thank you very much. Thank you for inviting me to speak here. I'm very happy to be back to Rio. I think I've been in Rio maybe 5 times and 4 times for math, and maybe second time. This is my second time in this series of conferences, and I'm enjoying it a lot. The conference, the city, it's wonderful. I will tell you about an exploration of the Hilbert-Smith conjecture in the context of symplectic dynamics. And maybe, just to start, a disclaimer, I gave this talk a few times before, so apologies to everyone who already heard it. But to my defense, I never gave this talk in Rio. Okay, so first of all, what is the Hilbert-Smith conjecture? So, to explain the Hilbert-Smith conjecture, it is good to start from Hilbert's fifth problem. So, from the year 00, namely 1900. So, Hilbert's fifth problem is a search for a topological characterization of Lie groups. So, more precisely, if a topological group, let's say G, is a topological manifold, which is somehow a topological property, so innate kind of topological property of a topological space. So, is it necessarily true that G is isomorphic, well, as a topological group to a Lie group? So this was Hilbert's question, and the answer has been known for a while, and the answer is yes. Yeah. So in particular, such a topological group is not only a topological manifold; it's also a smooth manifold. And so this was proved by a number of people. Maybe I will mention just von Neumann. Von Neumann, who proved the case of compact groups in the year 33, and also maybe I'll mention Gleason and Montgomery and Zippin, who proved it in general around the year 55. Okay, and maybe I will also mention a related work of Yamabe from 1953, who kind of explained when a group is a Lie group. So more precisely, a locally compact group, let's say, G is a Lie group. If an on-leaf, G has no small subgroups. Okay, so no small subgroups, probably it is better to say something like no system of smaller and smaller subgroups. So technically this means the following. So there is an open neighborhood of the identity that contains no subgroup. Right? So no subgroup of G. Okay, that is not the trivial subgroup. Okay. So here's a key example, and we will see that this example is somehow super important, of a group that does have this system of small subgroups. Namely, let's consider the group G to be ZP, so the topological group of periodic integers. Okay, so here are some useful facts about this group. So first of all, this is the completion of Z with respect to the periodic distance. So dp AB is the P norm of A minus B, where P norm of n, of an integer n, is P to the minus k, such that P to the k divides n, and P to the k plus 1 does not divide n. So it's the maximal power that P divides. And okay, fine. Also, P norm of 0 is just 0. Okay, and okay, one can pick any other constant bigger than 1 there, as long as one fixes it. Okay, so then this is a topological group, and in fact it is a compact topological group. Compact topological group. So clearly also locally compact. And now here's the sequence of small subgroups. So let's consider the following. Let's consider P to the k ZP. Okay, so this is a subgroup of ZP, no problem. And then we can write it as a closed ball. So it's all the periodic numbers of norm less than or equal to P to the minus k, of course. This is just by definition. But also one can write it as an open ball. So it's the same as all the x whose P norm is less than, let's say, P to the minus k plus 1/2 and strictly less. Sorry, strictly less. Yeah, so this is, these are both closed and open subgroups. Okay, and they form base of the topology at the unit 0. Yeah, so 0 is the unit of this group. Yes, so we look at the additive group. Okay, and maybe one more thing is that we can generate these numbers, these periodic numbers, as power series in P. Okay, so one can look at power series like this: AI P to the I, right? So P kind of, the power of P goes to plus infinity, right? Because somehow the higher power of P we get, the smaller it is in the norm. Yeah. Okay, where AI are some integers. Okay, so here's a way to generate all of them. This is kind of not a unique way to write a periodic number if you just without any requirements on the AI, but it's fine. So that's the only thing that we need. Okay, so indeed this is not a Lie group. This is a compact topological group, but but we have this sequence of small subgroups. So now the Hilbert-Smith conjecture is the following. So this is a conjecture from 41. So it's like Smith's version of Hilbert's fifth problem. So it is that a locally compact topological group, let's say G, which acts on a, let's say, connected topological manifold X, well, you know, one should require something from the action because every group can just act trivially, right? But so if it acts faithfully, must be a Lie group. Lie group. Okay, and maybe first of all, what is faithfully, right? So faithfully means that we get a continuous so we get a continuous monomorphism. Right? From G to homeo of X. So this is how it acts. Okay, so so otherwise it's kind of, you know, effective and continuous. And continuous, well, G is a topological group, and homeo X is also a topological group with compact open topology. But if X is, let's say, compact and smooth, we can just say, you know, let's just take the C0 metric on homeomorphisms, and then continuity means continuity in this metric. It's the same. Okay, so max over X, distance between phi X and psi X. Okay. Distance on the manifold with respect to any your favorite Riemannian metric, let's say. Okay. Now, so locally compact is technically a necessary assumption here because, you know, the diffeomorphism group acts. So and also connectedness is also important because you can take many copies of the same X and just have the product of groups acting on this. Yeah, so kind of like, for instance, you know, infinite dimensional torus acts on S1, disjoint union S1 many times. Okay, so what is known about this conjecture? So I'd like to survey some results before telling you why I started talking about the p-adic numbers here. Okay, so known. First of all, just this conjecture, as stated, is known for n equal 1 or 2. So kind of, maybe I should have said like n manifold of dimension n. Yes. Lie groups are finite dimensional. But, by the way, Lie group here can be something like S1 times anything discrete. So, okay. So somehow it's, so there's the identity component that matters. Okay. Right, so it's kind of, it's a group which is which smoothly locally looks like Rn. Okay, so this is known in dimension 1 and 2. Again, Montgomery and Zippin, 55, and for n equals 3, this is a result of John Pardon from 2012. Okay, that's all that is known about this question, right? So, contrary to Hilbert-Smith's problem, which is completely solved, this question is fully solved only for n equal 1, 2, and 3. However, nobody really said that we should prove everything for the whole group of homeomorphisms. Maybe for a smaller subgroup, it is easier to prove, and one can actually do it. Okay, so in this direction, there are a bunch of results. So let's specialize our action to take values in some subgroup of homeomorphism groups, where usually this subgroup was defined by regularity. So subgroup defined by kind of classical regularity conditions. So for instance, then it is just generally known by result of Bochner and Montgomery for C2 diffeomorphisms. So if we require a few derivatives, one can write Taylor series, and things become easier. Then there was a result of Riaposh and Shepin, who proved it for Lipschitz actions. Okay, you have less derivatives, so you need to work harder, but you can still do it. And then there was a generalization by Maleshich, where he looked at Helder homeomorphisms with sufficiently large Helder exponents, so slightly better than 1, but somehow. And this is more or less the limit of how far these methods go, but then there was also result of Martin for quasi-conformal actions, right? So quasi-conformal means that there is some differential inequality times some constant. Okay, so this is Jacobian, this is norm of the derivative. So also some condition on derivatives. And basically, then there was a kind of generalization of this by Emge, which maybe I will not comment on, but it's basically similar. Okay, so now this is really what is known, and maybe I will just say that all the proofs starting from this one, actually maybe even these two, so they all use the following reduction of the Hilbert-Smith conjecture to an easier statement, more kind of special statement. So for a given, let's say X and G, where G is a subgroup of homeomorphism group, so for given X and G, the Hilbert-Smith is true. So Hilbert-Smith in this sense, yeah, for actions taking values in this G. So this is true if and only if true for G equal to ZP for all P prime. By the way, yes, so P was prime all the way through. Okay, so true for ZP means that ZP does not admit a faithful action by homeomorphisms taken from G. Okay, and the proof of this uses somehow the solution to Hilbert-Smith problem plus the following beautiful result of Newman. So there's from 31, so Newman is not von Neumann. So the result is that homeo of X has no small finite subgroups. Okay, so somehow using this, one can always pull out a copy of ZP from any action which violates this. Okay, so that's all about the introduction to this question. Any questions at this point? Okay, so now instead of putting a classical regularity condition, how about we put a different regularity condition? So let's consider symplectic homeomorphisms. Okay, so M omega will be closed symplectic manifold. The dimension of M will always be 2n, and I will write once and for all that from now on I will consider symplectically aspherical manifolds. Okay. So here also M omega will be symplectically aspherical, just in case I forget to say it later. So symplectically aspherical means that omega evaluated on all spheres is 0, and also C1 evaluated on spheres is 0. Various things generalize to various greater classes of symplectic manifolds, but let's just stick with this convention. So, take standard T to N. This is already reasonable. Okay, so actually, even without symplectic asphericity, we have subgroup of Hamiltonian diffeomorphisms in the homeomorphism group. And we have, let's say, subgroup of symplectomorphisms connected to the identity in the homeomorphism group. Okay, so far these are just smooth diffeomorphisms. But then we can do the following. We can look at the closures of these subgroups with respect to the C0 topology. Okay. So definition, maybe I will even put it here. So definition due, as far as I know, to Bukovsky, Humilier, and Seyfadini. So Ham bar of M omega. So this is a C0 closure as written on the left. So this is the group of Hamiltonian homeomorphisms. Okay. And of course, one can also take the C0 closure of this group. It will be slightly larger in general. Okay, and so this group, this group has various interesting properties. So, for instance, as Vincent explained to us, if the dimension of the manifold is at least 4, then there exist Hamiltonian homeomorphisms with just one fixed point. And if phi is smooth and we're working in symplectically aspherical case, then you always have at least n plus 1, let's say, or couplings of the manifold plus 1. Okay, so there are various flexibility properties like so. There are also flexibility properties of a different nature due to Buchowski and Obstein. And maybe one simple flexibility property is the following. So let's consider a function on the open interval 0 epsilon to r or to r plus doesn't matter so much. So, and let's say that lambda is 0 near epsilon, but we're not saying anything about what happens near 0. So near 0, it can kind of just blow up or start oscillating. So it can be really wild. Okay, so in this case, lambda of norm z squared generates phi lambda Hamiltonian homeomorphism of, let's say, ball of radius epsilon inside Cn. Okay, and of course, then you can transplant this to sit in any Darboux chart in any symplectic manifold. So let me even erase this ball. Okay. Okay. And this happens no matter how wild lambda is near 0. Okay, just because near 0 you somehow make it constant, and then you make it constant again even closer to 0, etc., and the sequence converges because supports just shrink to 0. Okay, so this is a classical construction in the field, but this in particular means that phi in Ham bar in general satisfy no classical regularity. Right? Because you can just make all the derivatives blow up super fast. Okay. So this is a flexibility example, and here is maybe a rigidity example. So these are not all the homeomorphisms that one can imagine, because they preserve certain capacities, and maybe here's another one. So let's say M is symplectically aspherical. So this is again a theorem of Buchowski, Muller, and Sefardini. So let's say that B inside M is a symplectic copy of the radius r ball inside Cn. Okay, then Hamiltonian homeomorphism displacing the ball. Displacing B necessarily has C0 distance to identity bigger than R squared divided by some constant that depends only on the manifold. Okay. So again, M is closed symplectically aspherical here, but there are some generalizations. Okay, so these are the homeomorphisms we will consider. Okay. So here's the main result. Okay. So theorem from 2024. So Hilbert-Smith holds for Ham-bar M omega for closed symplectically aspherical manifolds. Spherical M omega. Okay, so maybe this is just a few reformulations. So no faithful actions of the p-adic groups. Or if G is locally compact and rho from G to Ham-bar is faithful, then G is a Lie group. Okay. So kind of these are just restatements of this result. But what we will actually be proving is the first restatement, as is by now the trend in proving this. And so kind of you reduce it to p-adic group, and then you restrict actions of p-adic groups. Okay. Maybe I will just mention that so two remarks. So first of all, via work with Marcelo Atala, on questions related to the C0 flux conjecture, we can generalize this result to certain simp0 homeomorphisms. So same holds for simp0 bar for certain symplectically aspherical M omega. For instance, M can be a product of surfaces where all the genera are at least one. So, for instance, it holds for the standard symplectic torus. And maybe number two is that one implies that we can recover original Hilbert-Smith in dimension 2. So for sigma G genus at least 1. So this proceeds by taking a p-adic action by homeomorphisms, then taking one of these subgroups p to the k zp, which is sufficiently small. This will sit on the identity component. Then you average the symplectic measure along this p-adic action. You check that the measure is sufficiently good so that you can apply Ox-to-Ulam theorem, and then you basically say that the identity component of area-preserving homeo is a Simp0 bar. And for Simp0 bar, we know. So, okay, and maybe final remark is that via arguments we worked out with Wilkins, but as you will see, this also follows from the proof that I will outline in a moment. Actually, in this case, so in the case of the theorem, ZP has no continuous raw, no continuous Ham-bar actions. Right, so somehow here we are talking about faithful actions. And here's a little bit more general, it's continuous. So this is just kind of rule out torsion. So rule out torsion. So finite group actions. That's the difference. Okay, so and then, you know, this means that if then you have a faithful action, then the group is a Lie group, and it's a torsion-free Lie group. Torsion-free Lie groups, one moment. Torsion-free Lie groups are contractible, and so there's basically a classification of such Lie groups. And in fact, if the action lands in smooth diffeomorphisms, or even C1 smooth diffeomorphisms, you can just say that the identity component of the group must be just RK, the additive RK, by restrictions on Lie algebra actions of Delzant. Yeah. Oh, yes. So a trivial action is trivial. So it has no non-trivial. Of course, trivial always exists. Okay. Wow. Let's see if this one is better. Oh, wow. Okay. That's a big improvement. Okay. All right. So I think these are some results. Well, maybe one more result. Since we're talking about symplectic manifolds, why not look at a symplectic version of this? So now, again, in the same situation, we also have no Hofer continuous actions. From ZP to Ham M omega. Here, okay, we don't require C0 continuity, we require Hofer continuity, but we pay for this a tiny bit, well, maybe a lot, I don't know, but we look at smooth diffeomorphisms. And this is still pretty difficult. Yeah. Yes. So the answer is actually yes, but this I will tell in just a moment. Actually, the answer is yes, and so you somehow need to replace Hofer by some sort of correct spectral norm, and then it is fine. In fact, even for finite energy, Hamiltonian homeomorphisms is going to be fine. Right. Okay, and now I'm mentioning this in particular because of the following result of Leonid Polterovich. And it is the following. So consider compact, semi-simple, p-adic Lie groups. So compact, semi-simple, p-adic Lie groups admit no homomorphisms. To ham m omega. Okay? So of course, one might think that these two results are kind of the same, because every p-adic Lie group has a copy of the p-adics. Okay? But the point here is that there is no continuity assumption on the homomorphisms. So no continuity. Assumption. And the proof goes by a result about automatic continuity of actions of such groups due to Polterovich, Shalom, and Shemtov from 2023. So the way you say, so if you have such a homomorphism, then it must be continuous with respect to the bi-invariant Hofer norm. And once it continues, okay, there is always a copy of ZP in the Lie groups, and okay, we just ruled it out. So this is the outline, and maybe theorem somehow 3 plus. So this one, I guess, is just somehow to appear. So to appear in paper we are writing with Leonid is that actually same holds for Hambar. Okay. So in fact this with something instead of Hofer, and this holds for all Hamiltonian homomorphisms. In fact, last time I gave this talk, a number of people at the same time asked me, whether this holds for Hambar. So today I can tell you that it does. Okay. Okay. So these are the results, and now I would like to describe some ideas of the proof. Are there any questions so far? Okay. So the ideas of the proof are a combination of classical quantitative symplectic topology plus a new equivariant Floer homology type result for this classical invariance, and a general idea about the p-adic numbers. So let me briefly describe all of them. So first of all, we use spectral invariance. So spectral invariance of Hamiltonian diffeomorphisms due to Viterbo, Schwarz, and O. So you pick a field, and then the spectral invariant of a, let's say, fundamental class with respect to the Hamiltonian diffeomorphism is infimum of action level A, such that fundamental class is represented by Floer cycle of action functional less than A. Okay. Second, we use barcodes, which in the setting we figured out with Leonid Polterovich in, let's say, 2016. So similarly to functions, as Victor and Bashak have explained to us, if you have a Hamiltonian diffeomorphism of an aspherical symplectic manifold, you can associate to it a barcode, let's say B phi, which is a multiset of intervals. So these are intervals, either finite interval like so, or infinite interval. So A, B, and so, let's say C. The starting points of infinite intervals are the different spectral invariants, where instead of M you put various homology classes. Mj are multiplicities, so positive integers. And this map is continuous in, let's say, Hofer distance. So continuous in suitable distances. And maybe one more point is that if we have an integer I, there's the degree I sub-barcode. So Bi phi inside B phi sub-barcode. Okay, of course, the barcode is just the direct sum over all degrees of the barcodes of degree I. Okay, so kind of a bar in the degree I barcode means that some class of degree I is born when you cross the starting point, and it disappears when you cross the ending point. Okay. And if phi, let's say, is non-degenerate, or maybe if it has finitely many fixed points, then this barcode is finite. So it's a finite multiset. In general, it can be infinite multiset. Okay. And next, ingredient is a theorem of Buchowski, Muller, and Sefardini from 21, again for symplectically aspherical manifolds. So first, the spectral norm. So gamma of phi, which is C1, let's say C fundamental class H plus C fundamental class, the inverse of H. First of all, does not depend on the Hamiltonian H generating phi. And second of all, is a C0 continuous, and extends to a norm on the Hamiltonian homeomorphism group. Right, so it is still non-degenerate, and maybe a comment. Gamma phi is bigger than some number, topological number epsilon phi, which is basically the capacity of a small ball that phi displaces. So for phi not not the identity. So I just write it like this to explain that this number does not depend on the field. So this is a geometric number. This one depends in general on the field. Okay, and furthermore, using something we proved with Kislev, so maybe end. So B phi and Bi phi. So Bi phi also kind of extends to Ham bar, and it satisfies the following property. So for all epsilon positive, so n epsilon phi, what Victor called B epsilon phi in his talk. I don't know why I wrote n. Anyway, so number of bars in B phi of length bigger than epsilon is this number is finite. Okay, so for all strictly positive epsilon. Okay, and maybe some more classical ingredients. So first of all, let's define beta I of phi to be maximal length of a bar in Bi of phi. So maximal of all of these beta i's, so beta, which is maximal beta I. This is boundary depth invariant of Michael Usher, and this is less than the spectral norm, than gamma of phi. Okay, so this is we proved with Kislev. Okay, so these are this is the classical input. So the other two inputs are the following. So the other input, so theorem, which I call maybe the iteration inequality. Okay, so this is a sharper version of an inequality we proved with Nicholas Wilkins. So it is the following. So let's look at the spectral norm of the eighth iteration of a Hamiltonian homeomorphism psi over Fa. So A is a new letter for a prime. because the letter P was already taken by the p-adic. Okay. so this wants to grow. It wants to grow linearly with iteration. It wants to be A times gamma Fa of psi. But of course, very often this is not the case. So you can easily construct even Hamiltonian diffeomorphisms, let's say supported in a small ball or something, whose spectral norms are uniformly bounded in all iterations. So there is an error. And the result here is that you can characterize this error. So here's one way to characterize it. There are some sharper ways to do it, but this is sufficient for the application. So this is sum of this beta I psi to the A, again with Fa coefficients. And I runs over a certain interval of indices. So I will write this interval once and somehow then more or less forget about it. So minus 2n a minus 1, 2n a, open left, closed right, minus the interval open left, closed right, 0 to n. Okay, so it's a scary interval, but the point here is that its length is linear in A. Okay, so this is the inequality. Its proof proceeds by equivariant Floer theory and quantum Synrod operations. I have maybe like 5 minutes since we started a bit later, so I will not explain more than this, but I can, I'm happy to explain later. Also, here the degrees are cohomological because it's more convenient for this formula, but it's not a big difference. Okay, and finally, the last ingredient of the proof is a general idea about the periodic numbers. So the idea is roughly that small subgroups generate large roots. So small subgroups, large roots. Okay, so the warm-up to this is that all integers a, let's say, that are not 0 modulo p are invertible in ZP. So ZP has many invertibles. So Z has very little invertibles, just plus minus 1. But ZP has many of them. So you just need the first term in the power series to be invertible, modulo p. Okay. And so the idea is that if rho from a group to some, let's say, a homomorphism group or any norm group is continuous with respect to norm, certain norm, we can get roots of, let's say, phi, which is rho of 1 of arbitrarily large order A, which can be taken to be prime, and let's say 1 modulo p. Now I'm reminding myself to stop. Okay, but all right. Yes, of arbitrarily large order, and well, such that the maybe roots psi a, such that the norm of psi a is basically the same as the norm of psi. So it's kind of bigger than norm of psi minus some delta. So delta arbitrarily small. Okay, and so then the actual proof is just combining this idea with this inequality and getting a contradiction to this finiteness statement. Since I'm out of time, I prefer to stop at the moment, but if you ask me, I can actually explain how to cook the proof. First of all, this idea is basically an application of inversion of power series, calculation of norms, and Dirichlet theorem on primes and arithmetic progressions, plus kind of continuity implying that on some subgroup p to the k ZP, everything is very, very small. So that's the delta. Okay. Now, how to prove the theorem? So let's apply general idea. Let's call it maybe star. So apply general idea for rho from ZP to Ham bar for a certain norm. So for certain norm, so norm, okay, gamma FA, where kind of here A, we don't know what A is yet. We will know it in a moment, but you can apply it by choosing delta for the C0 norm. So as we saw, here, the spectral norm is C0 continuous, but actually in a C0 neighborhood of the identity, it is just controlled by the C0 norm. So the proof of Vygotsky-Muller and Seyfadini gives you this. Okay, so it is uniformly, so all the spectral norms with all coefficients are uniformly serviced by this C0 norm. Okay. So then, so for delta very small, get a root psi, an eighth root of phi, where gamma fa of psi is bigger than, okay, so here, gamma fa phi minus delta bigger than this number epsilon phi we saw before, which is kind of completely geometric, minus delta. And when delta is small, this is bigger than, let's say, epsilon phi over 2. Okay, so we get a uniform lower bound on this psi, which does not depend on A. And then iteration inequality gives you the following. So it gives you gamma fa of psi to the A, but psi to the A is phi. So this is phi, plus some I in this interval of length linear in A of beta I psi to the A, but that is phi, bigger than A times epsilon phi over 2. Okay? And so, one more thing. This one is going to be less than a certain constant independent of A. We can arrange this by kind of restricting ourselves to a sufficiently large subgroup P to the k ZP. And these ones are smaller than this one, so they're also smaller than this constant. Okay? And so we get that this one grows linearly with some rate, and these guys are all uniformly bounded. Yeah? They're all uniformly bounded, and their number is linear in A as well. So it means that the number of such guys, which is of course a lower bound for n, let's say somehow eta phi fa, where eta positive, but sufficiently small, so somehow linear times this eta is weaker than linear times this epsilon over 2. Okay, so this guy must go to infinity, in fact, linearly. Okay, but on the other hand, our phi is fixed, and so this one is less than, okay, for A is sufficiently large, this is less than n, let's say, eta over 2 phi with q coefficients, but this does not depend on a, and it is finite, right? This is finite. So here is a contradiction which allows you to conclude. Yeah. So technically, what one does here is one breaks the sum into two pieces, those that are bigger than eta and those that are smaller, right? And then smaller ones you have at most linear, and bigger ones you have at most this number, right? This number, and each one contributes at most this constant. So, all right. So that is the proof.
More questions? Yes.
Could you get some of the version with high regularity by lifting the action to the bundle?
I think so. So yeah, I think so. I have not worked this out, but I strongly believe that this is possible. So I think I would say yes, some C1, something like C1. Yeah. Lipschitz, probably not, but I don't know. Almost, yes.
Further questions?
Yes. So I forgot to say. Oh, I forgot to formulate. So okay. Okay, I will write it. So generalizations. There are generalizations of this result. So here is a theorem we're working on with my student Margudiev, so in progress. So if M is symplectically Calabi-Yau or negative monotone, closed symplectic manifold, HS still holds for Hambar. So the negative monotone case, so there you already have C0 continuity of gamma and of Barkos due to work of Yusuke Kawamoto. You need to work a little bit more to actually prove this, but in fact you need to prove something a little bit sharper than just this. You need to actually look at the bars which you get. So this you can prove, and Calabi-Yau. So actually, exactly the same proof goes through once you know the C0 continuity of gamma, etc., which is something we figured out with Nicholas Wilkins how to do. Requires some extra argument. Yeah.
More questions? So let's thank Egor again.